Friends, today we are going to discuss from heat engine. It is a device which convert heat energy into mechanical energy. In a heat engine, working substance absorb heat Q1 from a high temperature reservoir at T1 and perform some mechanical work W. External work using a part of energy of Q1 then given out of the rest of heat energy to the sink Q2 at temperature T2. Now work done W equal to Q1 minus Q2. The efficiency of the engine eta equal to W by Q1 equal to Q1 minus Q2 divided by Q1. Eta equal to 1 minus Q2 by Q1, equation 1. Q2 equal to 0, then eta equal to 0 or 100% for ideal engine, which is not practically possible. This equation implies that no actual heat engine has 100% efficiency. Refrigerator. A refrigerator is a heat engine operated in the reverse order. It absorbs heat Q2 from the low temperature reservoir that is sink at temperature T2 when some external work W was done on it, and heat Q1 is rejected to high temperature reservoir at temperature T1. Now coefficient of performance beta for refrigerator is defined as beta equal to Q2 divided by W equal to Q2 divided by Q1 minus Q2 equal to T2 divided by T1 minus T2 equal to 1 minus eta divided by eta, where for Carnot cycle of engine Q2 divided by Q1 equal to T2 divided by T1 and eta is the efficiency of Carnot cycle. Eta equal to 1 minus Q2 by Q1, that is 1 minus T2 by T1. Thus, coefficient of performance of refrigerator depend on temperature of source and sink only, but not nature of working substance. Its value range from 2 to 6 for actual refrigerator. Carnot engine. A engine is a device to convert heat energy into mechanical work. In actual practice, the efficiency of heat engine is very small and ranges between 5 to 25%. This shows that at the most 25% of total heat energy supply is converted into mechanical work. So, Carnot device an ideal theoretical engine free from all the imperfectness of actual engine and never realized in actual practice is called Carnot engine. It is an imaginary engine and is taken as a standard honest which the performance of actual engine is adjusted. It consists of following parts. A cylinder with perfectly non-conducting walls but perfectly conducting base containing perfect gas as the working substance and fitted with a perfectly insulating and frictionless piston upon which wires can be placed. A hot body of infinite large heat capacity to serve as source of heat at constant temperature T1K. A cold body of infinite large heat capacity to serve as sink at constant temperature T2K. A perfectly insulating platform serving as stand for the cylinder. There the cylinder may be placed on any of three bodies. You can look at your picture. Next, Carnot theorem. The two postulates of Carnot theorem are: no engine working between two different temperatures can be more efficient than a perfectly engine working between the same limit of temperature between the same source and sink. All reversible engine working between the same limit of temperature have the same efficiency whatever be the working substance. Note, these two statements explain the reversible, that is Carnot engine, more efficient than irreversible, that is engine who is working between same limit of temperature. The efficiency of reservoir the efficiency of engine are equal and which depend on limit of temperature but not nature and properties of working substance. Proof. Source source 1, source 2. Consider two engine, one is reversible R and another is irreversible I, working between the temperature T1 and T2. T1 is greater than T2 as shown in figure above. There the quantity of working substance in the two engine is so adjusted that work done by I and R per cycle is same. Here irreversible engine is absorb Q1 amount of heat from source at temperature T1 and perform the output work W and reject Q1 minus W amount of heat to sink at temperature T2. Then the efficiency of reversible engine is eta I equal to W by Q1. That is an equation 1. Suppose similarly engine R absorb Q1 dash amount of heat from source at temperature T1 and performs the output of W and the eject Q1 dash minus W amount of heat to sink. The efficiency of reversible engine is eta R equal to W by Q1 dash. That is an equation 2. Let us assume the irreversible engine is more efficient than the reversible engine. Then eta 1 is greater than eta I is greater than eta R. W by Q1 is greater than W by Q1 dash. Q1 dash is greater than, obviously Q1 dash is greater than Q1. Q1 dash minus Q1 is a negative positive quantity. Now we couple these two engine I and R by a belt in such a way that the engine I is working as a heat engine, that is forward, and R is working as a refrigerator, that is backward, as shown in figure B. The source now lose Q1 heat to I and gains Q1 dash from R. Heat gained by the source Q1 dash minus Q2 dash. That is an equation. We can suppose equation 4. Then the sink gain Q1 minus W heat from I and loses Q1 dash minus W to R. Heat lost by sink Q1 dash minus W minus Q1 minus W. Q1 dash minus W equal to positive from equation 3. So external work done on the system equal to 0. Thus the coupled engine perform a self-acting machine without aid of working by external agency. Thus the coupled engine perform a self-acting machine without aid of work by external agency. Transfer heat continuously from a body at low temperature to a body at higher temperature. This conclusion contradicts the second law of thermodynamics and hence our assumption is incorrect. So finally we conclude that no engine can be more efficient than perfect reversible engine working between the same two temperature. Proof number 2. To prove the second part of the theorem, us replace the irreversible engine by another reversible engine R, proceeding as in the first part of the theorem, and on assuming the engine R is more efficient than the engine R, we will raise the stage that will contradict the second law of thermodynamics. Therefore, our assumption eta R is greater than eta dash R is greater than eta R must be wrong. Again, considering the engine R is more efficient than the engine R dash, we would obtain the same situation that will also violate the second law of thermodynamics. That means our assumption eta R is greater than eta R dash must be wrong. Hence, we can conclude that eta R must be equal to the eta dash R, that is eta R equal to eta dash R. Thus, this shows that all reversible engine working between same temperature limit are equally efficient. Thank you for today.